So let's begin the proof of theorem 2 about almost everywhere differentiability for continuous monotonically non-decreasing functions. And for this we introduce what are called the Dini derivatives. And if you take a point x in AB, interior point in AB, then the first one d plus f upper bar, this is equal to the lim sup as h tends to 0 of this expression fx plus h minus fx over h that appears in the definition of a derivative. But rather than taking the limit as h tends to 0, we take the lim sup as h tends to 0 where h is strictly positive. So h tends to 0 from above and you take the lim sup. So by definition this lim sup is equal to the limit of the supremum of this expression fx plus h minus fx over h, and the supremum is taken over all h in an interval 0 to delta, and then you let delta go to 0 from the right. So this is by definition this Dini derivative d plus f upper bar, and similarly one defines lim inf. So the second one is d plus f lower bar. This is lim inf of h tends to 0 with positive values. Similarly d minus f upper bar is lim sup as h tends to 0, but now h is less than 0, and d minus f lower bar, which is lim inf of h tends to 0 with the h taking negative values. So all these Dini derivatives, so they exist in the extended real numbers minus infinity to plus infinity, and f is differentiable at x, f is differentiable at x if and only if all the Dini derivatives coincide. So if and only if d minus f upper bar, so let's start with the lower, d minus f upper bar, so all of these are at x, then d plus f lower bar at x, and d plus f upper bar at x. So all of these, when they coincide, then f is differentiable because the limits will exist. If only the plus ones coincide, then f is differentiable from the right, and if only the minus ones coincide, then d is differentiable from the left. So if only these two coincide, then f is differentiable from the left, and if these two are equal, then f is differentiable from the right, and so on. And we also have some inequalities. So first one is that, so these are quite trivial, d plus f lower bar is less than or equal to d plus f upper bar of x, because one is the lim inf, the other one is the lim sup. And similarly we have that d minus f lower bar of x is less than or equal to d minus f upper bar of x. So these are the Dini derivatives, and we will show that for almost every x in this interval AB, so we can leave out a and b, the points a and b, because they are of measure 0, but we will show that for almost every x in this open interval AB, all these Dini derivatives coincide, and so the function f, when it is continuous and monotonically non-decreasing, it will be differentiable for almost every x in AB. I should also add here that it's not sufficient to have equality for all these linear derivatives for f to be differentiable. Since they exist in the extended real numbers, we should also impose that all of these are finite as well as that they coincide. So this finiteness is also important. So to show this, to show the proof of almost everywhere differentiability, we will make some claims. So these are 3 claims that we are going to make. So the first one is that all these linear derivatives are measurable functions. So this I am going to leave as an exercise to show that these are in fact measurable functions, using similar arguments that we used to show that the lim sup of a sequence of functions and the lim inf of a sequence of functions are measurable, except that here one has to choose, when h goes to 0, you have to choose a countable sequence. So this is not so difficult, and I leave it to you as an exercise. The second one claims that the upper linear derivative, the lim sup for the positive part, is finite almost everywhere in AB. And the third one claims that the d plus upper bar, meaning that the lim sup taken from for values of h strictly greater than 0, is less than or equal to the linear derivative d minus f lower bar, which is the lim inf taken. So this is the lim sup h tends to 0 from the positive side, and this is the lim inf h tends to 0 from the negative side. So the d plus upper bar is less than or equal to d minus f lower bar, and in fact 3, this point 3 implies that d minus upper bar f x is also less than or equal to d plus f lower bar x for x almost everywhere in AB. So this can be obtained by applying this third result to the function f tilde defined on the interval minus b minus a to r, given by f tilde x equals minus f of minus x. So when you take minus x, you land up in the interval AB, and so you can apply f, but then you also again apply a minus sign, and so the lim inf and the lim sups get interchanged and so on. So check this that 3 implies that the lim sup for the negative linear derivative is less than or equal to the lim inf for the positive side of the linear derivative for almost every x in AB. And now that we have these two, so we have this chain of inequalities. So this means, so 2 and 3 imply together that first d plus f upper bar at x less than or equal to the d minus f lower bar at x. So this is by 3, and then you have is less than or equal to d minus f upper bar at x, just because this is the lim inf on the left and the lim sup on the right, and then again by the consequence of this, so let me call this 3 prime. So this is by 3 prime, we have that this is less than or equal to the d plus f lower bar, and this is again less than or equal to the d plus f upper bar of x, and this is finite by the second part. So we see that we have a chain of inequalities where the left one and the right one coincide, and so all of these are equal. Yes, and for this holds for x almost everywhere in AB, and this will show the this will give us the result. So we will show first that the second part, that d plus f upper bar is finite, and then the third part for this inequality between d plus upper bar and d minus lower bar. So let's start with the proof of 2. So we have to show that the the positive dini derivative for the upper bar is finite for x almost everywhere in AB. And to show this, consider for a fixed lambda positive, the set E lambda defined as the set of all x in AB such that d plus f upper bar x is greater than lambda, and we will show that the measure of E lambda, the Lebesgue measure of E lambda, is less than or equal to fb minus fa over lambda. And so if we let lambda go to plus infinity, this implies that me lambda, well, the intersection of all these me lambdas, lambda positive, this is equal to 0, because the right hand side goes to 0 as lambda goes to plus infinity. But note that this is precisely the set E infinity, which is the set of points in x, set of points x in AB, such that d plus f upper bar is equal to infinity, positive infinity, and this is equal to the intersection of all these E lambdas. So this will show that me infinity is equal to 0. So we would have proven that the upper dini derivative is finite for almost every x in AB. So we will need to show this inequality, and to show this we will use the rising sun lemma. So apply the rising sun lemma to the function gx defined as fx minus lambda times x. So g is again a function from AB to R and defined with the following formula, fx minus lambda x. So the rising sun lemma implies that there exists a countable collection of disjoint intervals, relatively open intervals, ik, such that if ik is equal to ak bk, then g of bk equals g of ak, and if ik equals a bk, then g bk is greater than or equal to g ak, or g a. So in both cases we have g bk is greater than or equal to g ak, right? And if we write this inequality g bk greater than or equal to g ak, this is the same as saying that f bk minus lambda bk is greater than or equal to f ak minus lambda ak, which is the same as saying that f bk minus f ak is greater than or equal to lambda times bk minus ak. In other words, the measure of the interval ik is less than or equal to 1 over lambda f bk minus f ak. And now the set E 1 over lambda f bk minus f ak. Now on the other hand, the set E lambda is a subset of the union of all ik's k greater than or equal to 1, because remember that this was the set of points x in A, B such that d plus f bar x is greater than lambda, and since lambda is strictly positive, this means that there exists an h positive such that fx plus h minus fx over h is greater than lambda, which is positive, which means that fx plus h minus fx is positive, and so this belongs to the set E. X belongs to the set E used in the rising sun lemma. And this is on the right is precisely the set E. So each of these E lambdas is a subset of E. This means that the measure of E lambda is less than or equal to the sum of these ik's k greater than or equal to 1. This is simply by countable subadditivity rather, and then we have that this is less than or equal to k greater than or equal to 1 over lambda f bk minus f ak by the inequality that we just proved here, and this is less than or equal to 1 over lambda fb minus fa. So by taking a sort of a partition of the interval AB, you can fill in other points and make it this is a telescoping series, so that these terms fak and f ak plus 1 they will, or rather fbk and fak plus 1 they will cancel out, and you are only going to be left with fb minus fa. So I am going to leave this as an exercise. So this inequality where you move from the sum of fbk minus fak to fb minus fa, I will leave this as an exercise for you to check, and this shows what we wanted to prove, and this implies that measure of E infinity equals 0. So this shows that the upper Dini derivative, the positive one, is finite for x almost everywhere in AB. So now we come to the third part, which is to show that the upper Dini derivative for the positive side is less than the lower Dini derivative for the negative side for x in AB for almost everywhere. So to do this, we consider two rational numbers, capital Q and small q. So these are rational numbers, and we consider the set EQ capital Q, which is the set of all x in AB for which the upper linear derivative for the positive side is greater than Q, this capital Q is less than small q, and this is greater than the lower linear derivative on the negative side. So we will show that the measure of EQQ is equal to 0, which will imply that the union of the sets EQQ, the union over all rationals capital Q greater than small q rationals, this is also going to be 0, and this implies that the measure of the set X in AB such that D plus F X is greater than or equal to D minus F lower bar, this set has also measure 0, because this is precisely this union of the sets E small q capital Q, where you take the union over all rationals. And so this will show that D plus F upper bar is less than D minus F lower bar for X in AB almost everywhere. So to do this, we suppose that the measure is strictly positive, and we shall arrive at a contradiction. Now we start by taking by outer regularity, and since this number q over q is strictly greater than 1, capital Q over small q is strictly greater than 1, there exists an open set U containing E, and U is a subset of this open interval AB such that the measure of U is strictly less than measure of MEQ capital Q times Q over Q. So this is strictly greater than 1, this is strictly greater than 1, and so by this infimum property one can find such an open set for which this holds, because we have assumed this to be strictly positive. Now let U be written as a countable union of intervals in. So countable union, disjoint union of intervals, and we apply the rising sun lemma to the continuous function f tilde q, which is defined on the set minus in to R, and this function f tilde q on minus n is defined by f of minus x. So when you take minus x, you'll end up in in, and in is a subset of AB. So you can apply f plus q times x. So when you apply the rising sun lemma, this implies that there exists a set E minus en inside minus in such that minus en can be written, so first of all it's an open set, and it can be written as a countable union of disjoint open intervals. So countable union of disjoint open intervals minus ikn, where ikn is the interval akn to bkn, is a subset of AB, and so that we also have, so this is the shadow set in the rising sun lemma, where the sun rays don't hit, and whenever you have these ikn's, we have on ik minus ikn f tilde q of minus akn is greater than or equal to f tilde q of minus bkn, and f tilde q of x is less than or equal to f tilde q of y whenever x is less than or equal to y, and they both belong to minus in. So xy in minus in and xy, so x and x does not belong to ik, or rather minus en. So only on the end points of these intervals minus ikn we have greater than or equal to sign, and for the rest of the values outside minus en we have less than or equal to sign. These are the sets under points under the sun in the rising sun lemma. And if we unpack this inequality here, we get f tilde, so f tilde q is f of akn plus q times akn, which is greater than or equal to f of bkn plus q times bkn. And so this is the same as saying that f of bkn minus f of, so it should be minus here and also here, because we are taking f tilde q minus minus akn. So this is the same as saying that f bkn minus f akn, this is less than or equal to q times bkn minus akn, and this last term is nothing but the measure of ikn. So this is the first inequality that we get, and now we will again apply the rising sun lemma, this time on the set ikn. Now apply the rising sun lemma on ikn for the function fq defined on ikn to r, defined by fqx is fx minus qx, capital Qx. And so again by the rising sun lemma there exists a set ekn inside ikn. Ekn is a union, countable union of intervals, disjoint intervals ik and j. Ik and j are disjoint open intervals, and if ik and j is equal to the interval ak and j comma bk and j, then we have f of bk and j is greater than or equal to f of ak and j, and for any x which does not belong to this EKN. So this is the shadow set in the rising sun lemma. For y greater than or equal to x, we have f of y is less than or equal to f of x. So sorry, this should be FQ. This again should be FQ. So now let's try to unpack what this inequality means for FQ. So FQ BKNJ greater than or equal to FQ AKNJ. This is the same as saying that by definition f of BKNJ minus Q BKNJ is greater than or equal to f of AKNJ minus Q AKNJ, and this is the same as saying that f of BKNJ minus f of AKNJ is greater than or equal to Q times the measure of IKNJ, which is just BKNJ minus AKNJ.